And so understanding how to think about applying the material in a novel kind of situation. That's the kind of thing that's going to be most valuable in terms of those sort of conceptual kinds of ideas. Please take advantage of my office hours. I have office hours at least 1 hour every working day of the week. So just drop in and ask me questions, and I'll be happy to brainstorm things about the exam or any content questions you might have. Yes? An example that I've been using is trying to figure out in, say, a unit cell of some type, say the size of a hole that you might have. So which is not something we specifically went into in any of the calculations we had, but that is the kind of information you could get from the same pieces of information that you use to relate atomic radius to unit cell side length. It's just you're looking at a different part of the question. So if you have a simple cubic arrangement, for example, then asking what is the largest ion that could fit in the center of that unit cell without having to expand the corners away from each other. So does that give you an idea? So this is why I strongly suggest don't approach this material by trying to memorize equations or to memorize procedures, because chemistry is much more about there being general principles and there being ways to think about the problems, and then trying to, and then when you're faced with something you haven't seen before, figuring out these are the things that I know, how can I apply them in order to get myself to an answer. Okay, does that help? Okay. All right, any other logistical things before we get on to the content? Nothing from the chat? Yes. So the way I view every aspect of this course is that it contributes points to the final, to your final grade at the end. Okay, I don't even assign letter grades to anything. It's number of points. The reason for that is that there are some aspects of the class where essentially everybody is getting 100%. So the Newton-Alta stuff, as long as you keep at it until you show 100% mastery, you're getting 100% on it. The content videos, you have the ability to do that same thing as well. So but those are still contributing, 100 points each to the final grade. And so if I say, this is what a C is, this is what a B is on the exam, your final grade's going to be a lot higher than that because it's brought up by these other things, right? So what I am going to do is, when we are getting towards the end of the semester, I'm going to be looking at the grade cutoffs for the final grade that I have in the syllabus, and I'm going to be saying, do I have those set too high or not? And so at the final grade for the class, I am going to consider curving things because I have zero interest in the entire class getting a C or lower. I'm fine with if everybody ends up getting an A. That'd be great. And if that's the case, I will never curve the grade in the way where I am moving the grade cutoffs higher. But so what's in the syllabus is going to be the maximum I would have for the grade cutoffs, but very likely I will be dropping those down. Okay. Any other logistical things to talk about? Nothing from the chat? Okay. All right, so let's talk about some muddiest, oh, actually, I do want to do something before I get to the muddiest points. I want to point out something that I put up on Blackboard, a resource that I put up that goes through how to catalog the intermolecular forces that you have, either for an individual type of molecule or a pair of molecules. So I have here a step-by-step way to analyze it, along with, on a later page of it, some charts that where you have one molecule in blue, the other molecule that it's interacting with in red, and then what you do is you say, do I have an ion? If no, well, cross out the ion column and the ion row. Do I have a dipole? Okay, yes, maybe I have a dipole. Everything has induced dipoles, you leave that. Is there a hydrogen bond donor? Is there a hydrogen bond acceptor? If you don't have those, you cross those out. So those get crossed out. And the only things that are left, that are the gray ones, are the ones that you have. And so this top one is if you're looking at identical molecules. The bottom is if you're doing something like solubility, where you're looking at a comparison of different molecules that you have. And then in addition, in the same file, I have a bunch of examples that I go through looking at them. So I know that there's been a lot of angst over trying to figure out how to catalog which intermolecular forces you have in situations. And so I have put up this resource for you to be able to work with. Okay. Muddiest point. So a quick one here. What exactly does Torr measure? Torr is a unit of pressure. So it's like atmospheres, it's like Pascal, it's like bar, any of those things. And it's just on a different scale. So you may have also seen millimeters of mercury. The idea of this is that you have a barometer made of a pan of mercury. You have a tube that is inverted into that pan, and it's done in a way so that there's a vacuum at the top, so that there is no air up here providing pressure. Well, the height that the mercury rises to here is a result of the atmospheric pressure that is pushing down here, where there's no atmospheric pressure pushing in here. And so the height of the mercury from here is a measure of the pressure. 1 millimeter of mercury is 1 torr. So that's the way this works. And an atmosphere, standard atmosphere, is around 760 torr. So if you think about pressure as being what you're used to in the atmosphere, being 1 atmosphere, when you think about the vapor pressure of a solvent, unless you're at the boiling point, it's going to be significantly less than an atmosphere. And so in those contexts, using a scale like Torr can be convenient because you're talking about some small integral number of torr, maybe 20 torr, 30 torr, something like that. And that's sort of easier to work with in terms of the numbers than talking about, 0.05 atmospheres or something like that. So that's why Torr is sometimes used. Okay, we had a lot of muddiest points in a lot of different categories. So I've got, I think, 4 full pages of muddiest points here. A lot of them are on the colligative properties, and since we haven't spent a huge amount of time on those yet, I'm going to start with that. I am going to do the questions on kinetics last, if we get to them, simply because that's not going to be on this exam, even though there is a homework of it on it due. So we are probably not going to get to those today. But as always, the videos of these classes are recorded and posted with timestamps, so you should be able to find exactly the question that you want if you aren't going to attend today. Okay, so let's talk about colligative properties first. So, first question I have here is, how do you apply Van Hoff factors to colligative properties? So let's take a look at that. So we have a concentration, we have 4 colligative properties. We have vapor pressure lowering. We have boiling point elevation. We have freezing point depression. And we have osmotic pressure. So let's remind ourselves of what the equations are for these 4 colligative properties. We have the vapor pressure equals the mole fraction of the solvent times the pressure of pure solvent. We have boiling point elevation, so delta TB is going to be the concentration of the solute in molality times your boiling point elevation constant. We have an equivalent expression for freezing point, that is the molality of the solute times the freezing point depression constant. And we have the osmotic pressure is equal to gas constant times temperature times the concentration in molarity. Okay, so, and then the question is, where do we use the Van Hoff factors in these? The Van Hoff factor is a correction to the concentrations. Because remember that these concentrations are the concentrations of number of particles that you have in solution. So if you have NaCl, and if you're at a concentration where NaCl fully dissociates to make Na plus and Cl minus, then your concentration here is going to be twice, I here would be 2, twice the concentration of NaCl. So the M in here becomes your Van Hoff factor times your concentration of the concentration in molarity of the solute pre-dissociation. Okay, so that's the case for these 3. The mole fraction is a little harder because this is mole fraction of solvent, not of solute. So what you have to do here, it is number of moles of solvent, so X solvent, number of moles of solvent over the total number of moles of everything. So it's going to be number of moles of solvent plus the Van Hoff factor times the number of moles of solute pre-dissociation. Does that idea make some sense? Any clarifying questions on where to use the Van Hoff factors? Okay. All right. There is a very good question. Why does the presence of a solute lower the freezing point? There is, as I said in the video that discussed this, we are not going into that in this class because the concepts involved in it involves some concepts that we don't typically introduce until physical chemistry, a 300 level class that we have. There isn't as straightforward an explanation for it as there is for vapor pressure depression, boiling point elevation, and osmotic pressure. So I hate to have to put off that kind of question, but I think we would end up going down this really long rabbit hole that a lot of people would probably not follow, and it would just add to the confusion. And I apologize for that. So the general idea is simply at this point remembering that that the freezing point gets depressed, and I'm not going to ask you any conceptual questions about why. Okay, there were a lot of people that were having trouble with applying the colligative properties to find the molar mass of a solute. So I would like to go through an example of that. We will do this one here that is using freezing point depression, but we can do practically the same thing with any of the other colligative properties as well. So let's remember that for freezing point depression, we have delta TF equals concentration in molality times our freezing point depression constant. In this question, we are given the freezing point depression constant of 1.86 degrees C per molal. And we are told that we have 3.4 grams of the non-electrolyte. So this is the solute. So if it's a non-electrolyte, what does that mean our Van 't Hoff factor is going to be? Let's back up. What does a non-electrolyte mean? What does it mean for something to be a non-electrolyte? A little bit louder, please. It doesn't conduct electricity when you dissolve it. Correct. So if it doesn't conduct electricity when you dissolve it, that means it's non-ionic. It's a molecular compound. And so that means that the Van 't Hoff factor is going to be 1 because the molecule, the formula units you're using when you write down the molecular formula for this represents the molecules that are going to be dissolved. It doesn't separate into ions. Okay, I see the chat got that as well. Excellent. And we are told that our freezing point depression. We're saying that the water freezes at negative 4.5 degrees C. What is the normal freezing point of water? 0 degrees. So our freezing point depression is 4.5 degrees C. Okay. And we are told that we have 78.3 grams of water. So let's see what we can do here. We have this number, we have this number. We know that we don't have to modify M using our Van 't Hoff factor because it's 1. So we should be able to calculate M from this equation. So M is going to be our delta TF, which is 4.5 degrees C, divided by our KF, which is 1.86 degrees C per molal. So I will pull up a calculator. We have 4.5 divided by 1.86, and we get, we'll call it 2.42 molal. Okay. What is molal? molal means 2.42 moles of solute over kilograms of solvent, in this case, water. Okay, so how much water do we have? 78.3 grams. So if we take, remember that if we take a concentration, which is this, times whatever we have in the denominator, in this case kilograms of water, we get how many moles of solute we have. So 2.42 moles solute over kilograms water times 78.3 grams of water. And now we need to convert from grams to kilograms so that they cancel. So 1,000 grams water is 1 kilogram water. Okay, so my parentheses doesn't fit. Kilograms water cancel, that should be H2O. Grams of water cancel, and we are left with moles of solute. So we have our 2.42 times 78.3 divided by 1,000, and we get 0.189 moles of the solute. But we know how many grams of solute that was, right? So what is a molar mass? What are its units? I'm sorry? Moles over liters. That is a concentration in molarity. So what is the molar mass? Grams per mole, yes. And the chat has that as well. Excellent. So we have grams, we have moles. So our molar mass is going to be 3.4 grams of solute over 0.189 moles solute, which equals so 3.4 divided by 0.189, and we get 17.99 grams per mole. Okay. So again, I don't recommend looking at this as, okay, I need to find molar mass, let me memorize the procedure to follow for that. What I recommend instead is looking at it from the perspective of, we're told that there's a freezing point depression. I know this equation. Which pieces of information do I know? Which ones don't I know? I don't know this one, but I know the others, so I can calculate it. Once I have the concentration in molality, what does it mean? You figure out what it means, and then you see, okay, how can I use that with my other information to get myself step by step closer to what I was being asked for? And if what you're asked for is molar mass, which you know is grams per mole, you're given grams, so you need number of moles. So you look at this and say, okay, how do I get from a concentration to number of moles? And just by looking at what units need to cancel, you can figure that out. It needs to be, you need something that's going to cancel with kilograms of water, and you have grams of water. So that's the thought process that you would pursue. A clarifying question from the chat. If it wasn't a non-electrolyte, how would you find the Van Hoff variable, the Van Hoff factor? So If you are at low concentration, you can estimate the Van 't Hoff factor by looking at how the ionic compound breaks up. So this example we showed earlier for sodium chloride, you know that it breaks into 2 ions, and so you would estimate it as a 2. Now that is the maximum that it will ever be for sodium chloride. If you go to high concentrations, then you start to get the ion pairs, and so it will be somewhat lower than that. Exactly how low? We don't have a way to determine that at the general chemistry level. So you would have to be told what the Van 't Hoff factor would be, if it needs to be more accurate than the estimate you get by splitting it up into its constituent ions. Okay. You're welcome. Any other clarifying questions on this kind of, this kind of colligative property calculation? Okay. All right. Normal freezing point of benzene is 5.5 degrees C, and you're given a Kf. What's the freezing point of a 0.09 molar solution of a non-volatile electrolyte in benzene? So that is just like the first part of this question here. So, so you have a molality, you just plug that straight in. You're told it's a non-electrolyte, so you don't have to worry about the Van 't Hoff factor. You're given the Kf, so you just multiply the 2 to get your change in freezing point. Okay. Then whatever that change in freezing point is, you subtract it from the normal freezing point to find what the new freezing point is. So, so this kind of question here is extremely straightforward because you multiply these 2 numbers together and you subtract it from this and you're done. Okay. Okay. Continuing with colligative properties, there is an example question somebody wanted to do on osmotic pressure. So we will, let's see, we will, that's not quite on there, okay. Let's start by writing down our osmotic pressure equation, RT, concentration in molarity, okay? So we have the osmotic pressure of human blood is 7.6 atmospheres. We have our gas constant, which we can look up. So let me do that. Actually, I will do that here. I do not have these memorized. And it's convenient to use, when you look up the gas constant, it can be expressed in all sorts of different kinds of units. Since we're looking at atmospheres here, it's convenient to pick one that uses atmospheres as its unit. So I'm going to pick the one that says 0.08205, and that's in units of liters, atmospheres per mole Kelvin. Okay. Our temperature is, we are told, is 37 degrees C. We need that in Kelvin. So 273 plus 37 gives us 310. So 310 Kelvin times our concentration in molarity. So we now solve for our concentration in molarity. So we divide both sides with these things. Those cancel. Our atmospheres are going to cancel, and we're going to be left with moles per liter once that's over on the other side. So 7.6 divided by 0.08205 divided by 310 gives us our concentration of 0.299 molar. Remember that molarity is moles solute, in this case glucose, per liter solution, in this case blood, or actually we'll just say solution because we're making a solution. So we want to make 1 liter of this solution. So since this is per liter of solution, that means we need 0.299 moles of glucose. And it's asking for the mass. How do we go from moles to mass? What's our conversion factor? The question itself sounds like the answer. How do we go from moles to mass? The molar mass. So remember, molar mass is grams per mole. So we are told that glucose is C6H12O6. That's all. Okay. So you can get this very precisely by looking up the numbers for these. I'm going to do a less precise version from memory. We have 6 times 12 for the carbons, which is 72. We have 12 times 1 for the hydrogens, for 12. And we have 6 times 16 for the oxygens, 6,396. So we have 0, carry the 1, 16, 17, 18, 180 grams per mole for glucose. So we multiply this by 180 grams of glucose per 180 per mole of glucose. Moles cancel. And so we have 180 times 0.299. So you need 53.8 grams of glucose dissolved in your water to get the same osmotic pressure that you would have in blood. Okay. General idea makes some sense? So the procedure here, the procedure used to think about this question is just like the other one. You see that it's an osmotic pressure calculation, so you write down the equation for it. You figure out which pieces of information you have and which ones you don't, and there was only one you didn't have, so that's the one you calculate. And then you see, how do I get from that result to what it's asking for? Well, if you have a concentration and you have a volume, you can get to how much solute you need relatively easily just by dimensional analysis. Okay. All right, any clarifying questions on this? Okay. All right, we have another example here, molar mass of sugar. So this is just like the freezing point depression one we did before, so I'm not going to actually go through this one right here, but you simply use this expression for osmotic pressure to find the concentration and molarity. Once you have the concentration and molarity, you compare it to the other pieces of information that you have. Here you have a mass in a volume, and so you go from mass in volume, and you compare that to the molarity so that you can get the number of moles. Okay, so again, it's just dimensional analysis at that point. Same kind of issue down here. So actually, I think that one is an exact duplicate of the other one. Yeah, I think so. So yes, so multiple people got that. Okay, this question here. So we've been talking about the freezing point being, the freezing point depression being the freezing point constant for the solvent in question times the concentration and molality. But at the CIC, they say to use this expression. So the only difference between the expressions is that this expression includes the I, the Van 't Hoff factor, directly. And so, and this expression is assuming that you remember that the molality that you're dealing with, the concentration that you're dealing with, is concentration of particles. So you have already multiplied by the I if you needed to. So they're really the same thing. It's just a question of whether it's explicitly showing the I or not. Okay. There was a conceptual question talking about the vapor pressure depression that was saying, okay, I can understand why the rate of evaporation decreases when there's solute present because it's blocking the molecules from getting into the vapor phase. But why doesn't the rate of condensation change too? And so let's look at that by looking at what's going on the surface of our liquid sample. So we've got our solvent molecules in here. We have a few solute molecules, and it's a non-volatile solute, so we have some solvent molecules that are in the vapor phase that are coming down and either bouncing off the surface or potentially losing enough kinetic energy through the collision for them to condense into the liquid phase. And so the idea of the vapor pressure, the evaporation rate going down is that if the surface is blocked by these solute molecules that are too heavy to vaporize, then that is one region of the surface that cannot escape into the vapor phase. So if this comes up with enough energy to be able to vaporize but runs into one of these molecules, it loses that energy through the collision, and so it doesn't evaporate. So you have fewer molecules getting into the vapor phase. Now, the process of the molecules coming in and hitting the surface, that is a collision as well. And the condensation happens when it hits and transfers some kinetic energy to one of these molecules, so that now that molecule that hit the surface doesn't have enough kinetic energy in order to escape back to the vapor phase again. So it comes down and hits, and then you have sort of a little bubble of extra energy here that then dissipates and spreads through the rest of the solvent. Well, that same thing can happen if it hits a solvent molecule as if it hits one of the solute molecules. It can still lose its kinetic energy to that molecule. The only difference is that this molecule can't in turn gain enough energy for it to evaporate. So that doesn't happen. So the condensation rate doesn't change because the whole process of condensation is a loss of solvent molecule kinetic energy, and that can happen regardless of what it ends up hitting. Okay. Any clarifying questions on that idea? Okay. All right, we're going through these at a faster clip than I expected. I'm happy with that. Okay. Does osmotic pressure work the same way when a gas is the solute? That's an excellent question. So in theory, yes. In practice, it is very, very difficult to get a semi-permeable membrane that is impermeable to dissolved gases. So in practice, it doesn't really work the same way because for osmotic pressure to work, your solute has to not be able to pass through the semipermeable membrane. And it's very difficult to get a semipermeable membrane that will block dissolved gases. Okay, any clarifying questions on that? Okay, that's a very astute question though. All right. When dealing with the colligative properties, do the units have to be specific ones, or do they just have to be consistent for the problem? For example, Torr versus atmospheres. So that would be related to vapor pressure lowering in particular. Well, so in this case, in all cases with units, what you should do is write the units in. And so that will tell you your answer when you do it. So if you are given the vapor pressure of the pure solvent in atmospheres, then when you use this equation, you end up with the vapor pressure of the solution in that same unit, in atmospheres. If you were given it in Torr, you get it in Torr. Now, down here, for example, when we did the osmotic pressure example earlier, I carefully chose the units of R to be the same units I was dealing with for the osmotic pressure. We were given the osmotic pressure in atmospheres, so I chose the value of R to already be in atmospheres. And so the solution to this question of which units do I use is just write the units down and see what cancels. And if you end up not having things canceling, then you need conversion factors to make them cancel. Okay? Every intermediate step you use should have the units written down, because that will prevent nearly all mistakes that you can make, and it will guide you towards how to solve the problem. Any clarifying questions on this? On units in colligative property calculations? Okay. All right. So a couple of people asked this very simple this question here, which is going to have a higher boiling point: a 2.5 molal aqueous solution of sodium chloride or a 2.5 molal aqueous solution of potassium chloride. Okay, there are two levels of theory that you could use to estimate, to evaluate this. The simple version is saying that sodium chloride and potassium chloride, so sodium chloride is this, potassium chloride is this. In both cases, they dissolve into two separate ions. So our estimate of the Van Hoff factor is going to be 2 in each case. And so you would look at this, this question and say, well, if the Van Hoff factor is the same, and if the concentrations are the same, then the freezing point, the boiling point elevation will be the same in both cases. So that's the sort of first approximation answer to the question. The more sophisticated answer to the question is that 2.5 molal is pretty darned concentrated. That's in 1 liter, that's 2.5 moles of your solute. And so for, let's see, potassium chloride, what's our molar mass of potassium is, if I can see correctly, like 40 or 39, chlorine's 35. So we're looking at 75 grams times 2.5 in a liter. That's a lot. And so the Van Hoff factors are actually going to be different from 2, aren't they? The Van Hoff factor is going to be less than 2 because you've got a lot of solute in there. And so the question is, which of the two, sodium or potassium is going to more readily form these ion pairs that in solution that are causing the decrease in that are causing the decrease in concentration, reducing the Van Hoff factor. So the main difference between sodium and potassium is that sodium is smaller, right? Potassium is the next period down. And so because of that, sodium has a more concentrated positive charge. That single positive charge is in a smaller volume than the single positive charge in potassium. And so because of that, the attractive forces between the sodium ion and the chloride ion are going to be slightly stronger than the attractive forces between the potassium ion and the chloride ion. And so because of that, you will have slightly more ion pairs formed in the sodium chloride case. And so it will have a lower I. So I for sodium chloride will be less than I for potassium chloride. Okay. And so that means that the boiling point elevation for potassium chloride is going to be higher than the boiling point elevation for sodium chloride. Now, is it going to be a huge difference? Probably not. I mean, my guess off the top of my head about the I's in these cases would be probably something like 1.4 versus 1.5, something like that. So it's not going to make a huge difference, but it will probably be a measurable difference. And so the question is going to have to be, I mean, I know this question came from Newton, and I strongly suspect that the way the question was worded in Newton, it probably wasn't clear enough about which level of theory it was going to be asking for. And so on an exam, I would be very clear about that kind of question so that you would know how deeply you need to go into the analysis. Okay, any clarifying questions on this issue, the application of boiling point elevation for equimolal concentrations, or the extra issue of subtle differences in Van Hoff factor? Okay. All right. I'm going to come back to fractional distillation if we have time. Phase change question. How does size of molecule affect boiling point? Okay. So there are several factors that go into this. One of them is that the larger the molecule, the more electrons that you have, and so as a result, the stronger the London dispersion forces that you have, and therefore the stronger the intermolecular attractions, which is going to decrease the vapor pressure. Decreased vapor pressure means an increased boiling point. So due to London forces, the larger the molecule, the higher the boiling point. The other issue is that if you just think about it in terms of momentum, mass that you have, if you have a large mass, you need more kinetic energy applied to that mass in order for it to get the velocity necessary to get into the vapor phase. Okay, so there's this inertia issue associated with the molecules. So larger molecules, for that reason as well, will tend to have a higher boiling point. Finally, if by large you're meaning long, like if you're comparing, like hydrocarbon chains. So I'm going to leave off all the hydrogens that are going on here. If you're comparing like a 3-carbon chain to like a 5-carbon chain, or even longer. The longer the molecule is, the larger the surface area you have where the molecule can then nestle up next to an adjacent molecule, and so the attractive forces that you feel are going to be stronger because the distance between them is smaller. So remember that Coulomb's law has the force of attraction, or the force being charge 1 times charge 2 over the distance between the two charges squared times some kind of proportionality constant that we're not going to worry about. And so if the R's are low, meaning that the things that are causing the attractions are really close together, then you end up having stronger attractive forces. And where that comes in is if you have a long molecule like this versus something that is more spherical, you have fewer points of interaction here than you do here. So for at least 3 reasons, the larger the molecule, the higher the boiling point. Okay, any clarifications on that? Okay. All right, solubility. How is molecular polarity related to solubility? So that goes back to what I showed towards the beginning of class, where we were looking at this chart that I have put up onto Blackboard. If you have a dipole moment, which means polarity, then that means that you have the possibility of dipole-dipole interactions, dipole-induced dipole interactions, and so on. The more polar the molecule is, the stronger those forces are going to be. So that's essentially what's going on here. Molecular polarity is related to solubility in that dipole-dipole, dipole-induced dipole interactions, those kinds of things are stronger in cases where you have a polar molecule than where you don't. And so remember that when you are looking at solubility, what you have to do is, let's see here, you have solute-solute interactions, you have solvent-solvent interactions, and you have solvent-solute interactions to think about. And so if these are strong and these are both weak, then these are not going to split apart in order to allow these molecules to come in between, right? So determining what's soluble in what is a question of looking at what forces do you have here, what forces do you have here, and are they the same forces as what you have here? And if they're the same types and same strengths roughly, then it's absolutely okay to form these at the expense of some of these. But if there is a significant difference between them, then it's not going to happen. So what it comes down to is cataloging the forces you're dealing with and comparing them, and then using the like dissolves like idea. Okay. Any clarifications on that? Okay. How do insoluble salts work, and why are they insoluble? That's a fantastic question, which we haven't gone into before. So the idea is that if you have a salt, so you have anions and cations, anions, cations. So we have here a small little crystal, okay? And going into solution means that you are now putting the ions into a solvent medium. Okay, so red is going to be our solvent. Usually when we're talking about ionic compounds, we're talking about dissolving them in water. So, so probably water in this case. There we go. So determining whether a salt will dissolve into water is really about what are the attractions of the water molecules for these ions like compared to the attractions of the ions for each other. Now, salts, there are some salts that are extremely soluble, like sodium chloride. You can make salt water pretty easily, which means that the dipole ion interactions that you have in the water are pretty strong. And they're strong compared to the forces that are holding the ionic crystal together. But other types of ions, like silver chloride has stronger ion-ion interactions in the salt and or weaker salt ion dipole interactions in the solvent. Okay. So that's generally what's going on. And so if you think about it, silver is extremely large, extremely polarizable. It has a lot of electrons in it. So here, in this case, you probably have a lot of ion-induced dipole forces that are contributing to the strength of the attractions in the solid phase. Now, I do not expect you to be able to predict which ion pairs are soluble and which are not. I don't expect you to be able to predict that at all. But you should be able to, if you're told that this one is soluble, this other one is not, you should be able to explain what that means in terms of the forces here or versus the forces here. Okay. Any clarifications on that idea? Okay. All right. We have some questions. We have a question on concentration. From the activity, how do you convert molarity into ions? Okay, so let's talk about this one. This one we can do pretty quickly. So let's suppose we have 10 to the negative 6 molar. Okay, that is moles solute per liter solution. And what we are trying to, so 10 to the negative 6 of that. What we are trying to get is the volume in which there is a single ion, right? So, so what that means is we take this and we do 1 over it so that we flip the units, right? So we have volume per mole, and then we go from moles to ions. So if we do 1 liter of solution, 1 liter of solution over 10 to the minus 6th moles of solute, okay, that becomes 10 to the 6 liters solution per mole solute. Then you have to go from moles to atoms. So 1 mole of the solute is 6.022 times 10 to the 23rd ions, because what we're talking about here, the solute is an ion, okay? And so you just then take 10 to the 6th divided by this to find out the volume you need in order to have a single ion. So again, this is just dimensional analysis. Okay. All right, I've got about 5-ish minutes. So before getting to the kinetic stuff, there was one question I skipped on fractional distillation. So I know that there is a little bit of information on this topic in the textbook, and are there Newton questions on it? Anybody know? Have there been? Haven't seen any? Okay. So I'm not going to be asking anything on the exam about fractional distillation. I will very briefly talk about the idea of it because it is an extremely useful technique, but I'm not going to, but we're not going to go into incredible detail on it. So the general idea, let's suppose we have a mixture of two liquids, benzene and toluene. Okay. A distillation setup is one where we have our mixture here. We're applying heat to it, so we have our flame down here. Probably have a thermometer stuck in here, and this is sealed off. And there's a tube that comes down into a water jacket, which cools off the vapor. And then the vapor condenses into liquid droplets. So we have evaporation happening here, condensation into liquid droplets that come down here into another flask. Okay, and so we have the collection happening over here. Now, benzene has a higher vapor pressure than toluene. And so if we look at a plot here of mole fraction of toluene going from 0 to 1, we get something that looks kind of like this. And I'll explain what this is in a second. So this is the liquid, this is the vapor. And let's suppose we're starting at a 50-50 mixture, so 0.5 of benzene and toluene. Okay. Because at this, so this here is temperature going up this axis. So this here is the boiling point of pure benzene. This here is the boiling point of pure toluene. And the boiling point of the mixture is in between those. Okay. If we draw a line across here, because the vapor here is at the same temperature as the liquid here, this gives us the composition of the vapor phase. And so we find that this is about 0.2. So the liquid here is 50-50 benzene and toluene, but the vapor is 20% toluene and 80% benzene. And so what we get collected down here is now enriched in the benzene. So 80% benzene, 20% toluene. So with that idea, can we do better than 80%, 20%? Well, if we start, if we do this once and then take this and put it here instead and then vaporize it, then you're starting right here, you go over, and then the next step you have about 98% benzene and 2% toluene. Okay. So so you could do that by then putting a flame under this and having another condenser that comes down this way. Or you can do it by expanding this range, the space between here, and allowing it to cool down as it goes up. And what happens when you do that is that if we zoom in on that region, then the vapor that's coming up, which is 80% benzene, 20% toluene, it's going up into a cooler region and it's going to condense into droplets on the walls, right? But then that can revaporize. So this right here is the 80-20, but the benzene is going to evaporate more. And so up here, when it recondenses again, it's going to be the 98-2. It's going to, then that's going to evaporate, and you're going to end up getting basically 100% after that. So that is fractional distillation, which is a way to take advantage of this kind of plot here through multiple distillation steps, but just along the column, so that you can get pretty pure stuff here. I'm not going to be asking too much about that, but since people were bringing that up, I thought I would address it. Okay, so on the muddiest points, we got through all of them except for the kinetics ones. I will make sure that the kinetics ones get added to the top of the list for tomorrow's class. And so if you had any of these questions, and if you're not going to be tuning in tomorrow, make sure you check out the video for tomorrow, and I will have timestamps on there for exactly which questions answered where. Any last clarifications? Oh, so somebody here did say there was a Newton question that was very specific about fractional distillation. Okay, again, this is one of those cases where I wish I were able to pull out and remove specific questions from Newton, and I don't seem to be able to do that. So if somebody wants to send me that specific question on Piazza, I can try to address whatever that specific question was on that forum. Thank you all. Yes? What are you allowed to use on the test? Basically anything other than each other, other than asking LAs or the CIC, how do I do this specific problem? It's open resources.
Will we be using one of like the proxy things?
Using oh, you mean like one of the, like ProctorU or something like that? Yeah, no. I still am not sure if it's going to be on a Blackboard test or a Newton test, but it will be timed so that when you start it, you're going to have 3 hours to complete it. I'm designing it so that it's only going to be an hour and a half worth of work, but I don't want you to feel the time crunch on it, so I'm giving you 3 hours, single sitting. The clock will start when you open it, and you'll have 3 hours at that point. Okay? But you should be able to do it anytime within that 3-day window. Any other clarification questions? Will the test be multiple choice or short answer or both? I'm not going to be doing short answer because I don't feel like I should be asking you questions that require my manual grading when I am already behind on manual grading of other things. So, so this test will not have any short answer. There will be calculations to do, so there will be numerical answers you put in. I will be very specific about whether you have to type in the units or not, so that there are no worries about that. There will be multiple choice. There may be like matching or various things, but stuff that can be automatically graded so that you will get your results quickly. You will not need, a good question here, you will not need to turn in your work. When there is a progression in a long kind of analysis or calculation, I am going to have you, I'm going to be asking intermediate questions along the way so that you can get partial credit if you do part of it correctly, but it's not going to be, you got the wrong answer and now I'm going to pour through your work to see how you did it and see the partial credit there. How many questions? I don't have the answer to that just yet. I am still in the process of writing the thing. Okay, thank you all, and yeah.